Hello, my dear. Welcome to IMS GATE Academy. I hope you are all good and your preparation going to be in right direction. I am Pragyabrat Tripathi, and we will continue with the lecture of thermodynamics, right? So we will already covered in the previous classes. We already covered the thermodynamics process. But what we learn to this discussion, see beta, we know that the thermodynamics process for any process, thermodynamics process, this is for any process, okay? So what we learned already, we learned that, sir, see, we have equation like that. See, this is we have equation, very important. What is that? dq is equal to dE plus dW. This is precisely first law of thermodynamics. Work and heat interaction only, right? So we can write like that, sir, this dq minus this dW gives a property, change in a property. This is the system property, change in a total energy. So this is your transfer and this is your change. So transfer of energy, that means this is your transfer of energy of this is your transfer of energy and this is your change in energy. Change in energy. Okay. Change in energy. 1 second. Change in energy. Okay. So this is your change in energy, and this transfer of energy, it is a boundary phenomenon. What? This is your boundary phenomenon. Boundary, and this is your system property. This is your system property. This is your system property. So very clear about that. This is the change in energy and this is your system property, right? Now, if you apply this process, when we apply for the, so what is the assumption of this one? First, we discuss the assumption of this equation. So if you assume this equation is valid, energy equation, this is your energy equation, energy of closed system, very important, closed. Why it is closed system? Why this energy is a closed system? Why? Because there is only transfer phenomena. Transfer either in the thermodynamics beta, we have to do the transfer in three mechanism, or all the three, or any of the two combination, or any one of the combination. We transfer heat, work and mass. So if we transfer, if you disregard the mass transfer, so that and remaining is the transfer in the form of heat and work. So if disregard the mass transfer, so there is no chance of open system. So this is for a closed system, okay? And it is a property, right? Energy of a closed system. This is your energy of a closed system. Energy of a closed system, and it is a property. It is a property. Okay, it is a, yes, it is a property. It is a property. That means amount of energy, stored, amount of energy stored in a system. This is what amount of energy stored in a system, and it is a point function. Okay. So we already discussed of this thing. These things already we already discussed. Okay. So this is precisely the first law of thermodynamics for any process. Now, okay. So and we also discussed the, if we write dE is equal to du, that means change in the total energy is exactly equal to the change in internal energy in the form of intramolecular energy for the stationary system. For the stationary system. So dq is equal to du plus dw is applicable for the stationary system and closed system with equilibrium condition. So we have to write like that. What is that, beta? See this one. Okay. Now the equation is like that. So if dq is equal to du plus dw, this is also a first law of thermodynamics for a process. Okay, we can write also dq is equal to delta u plus w for the process 1 to 2. Q 1 to 2 is equal to u2 minus u1 plus w1 to 2. Okay, so these equations are the first law of thermodynamics for a process, and this is valid. This is for first law of TD for any process. Very important. For any process. Why it is any process, beta? Anyone please? Why it is any process? Anyone please? Why it is any process? Beta? Why it is any process, please? Why it is any process? Why it is any process? Anyone please? Why it is any process? Just go through the concept. Why it is any process? See, I give you one trick for that one. Yeah, this is the trick for that one. What is that? This is for any process. Why? Because see, beta, during the process, which process? Process 1 to 2, process 1 to 2, that means if this is our thermodynamic plane y and x, and this is point 1 and this is point 2, state point 1 and state point 2, and you have to go from 1 to 2 for any process, either with the reversible or either with the irreversible. Any process. That means if we defined reversible, that means there must be a defined reversible work. That means if we write like that, beta, if you defined this W like integration 1 to 2 P dV, that means now we have to define the work. That means we define the energy interaction as a reversible manner. So the equation Q1 to 2 is equal to U2 minus U1 plus integration 1 to 2 P dV. So this equation this equation is applicable only for the reversible process. Why? Because work you have to define. This is for the reversible process only. Yes or not? A reversible process only. So this equation. So, but the in this box, we are not able to define which manner the energy will interact. Good afternoon, Atul. In which manner the energy will interact, either in reversible or either in irreversible. Interaction, that means transfer. Interaction, energy interaction, that means energy transfer. Energy transfer, it is a boundary phenomena. So which process the energy will interact from the surrounding to the system, yeah, system to the surrounding. That means interaction of system and surrounding, in which situation, in which process we are not able to here define still here. Why? Because this is dW. dW is anything. Work transfer is anything, either reversible manner or either irreversible manner. So this equation is applicable. But once you define the energy transfer with a reversible manner, so this equation is applicable for the first law of thermodynamics for a reversible process. So this equation is applicable for reversible process only. Okay, this equation is applicable for the reversible process only, right? And also, what is the second assumption of this equation? The second assumption of this equation is, what is the second equation? This is your closed system. Closed, yes. Why? Because only heat and work will transfer. There is no any transfer of mass. So this is closed, very important, and stationary. Why it is stationary? Why it is stationary? Why? Because the energy, the total energy, in the total energy, very important beta, in the total energy, this total energy is the component of intramolecular energy plus kinetic energy plus potential energy. Once we disregard the total energy, a component of the energy with respect to the kinetic energy and potential energy, and only we consider the energy in the form of intramolecular energy, in that situation the total energy is equal to intramolecular energy for the stationary system. For the stationary system. So this is for the stationary system and stationary system at equilibrium. System at equilibrium. Clear? So this equation is the station. These 2 points are very important. These 2 points are very important, beta. One you solve, once you can analysis the first law of thermodynamics, where we can apply. See, beta, in whole engineering, when you apply the equation, just to go through that, the under which condition this equation is applicable. This is a very important aspect of the studies. You cannot apply any equation for anywhere. Like a Bernoulli's equation, you can apply only a streamline, along the streamline. It is not at any point, along a single stream. That means if you take a point at streamline 1, streamline, there is a fluid is flowing, and there is a, let's suppose there is an infinite number of streamline. So we select imaginary streamline at point 1. In that imaginary streamline, same streamline will select point 2, and we can apply that equation. And that equation will also applicable for the non-viscous. So under which condition any equation is applied, that is the very strong concept for the engineering point of view. You cannot add. It is not like a mathematics. It is also engineering. This is not only mathematics. Like that, PV is equal to MRT. This is the state postulate equation. This is the state postulate equation, PV equal to MRT. That PV equal to MRT we can apply for anywhere, for any process. Why? Because Why? Because PV is equal to MRT is the property. P is the property, V is the property, T is the property. So we can apply for any process. Either the process is reversible or irreversible, but only for the ideal gas, not a real gas. You cannot apply this equation PV is equal to MRT for the real gas. So these are the limitations. So at that point of condition, the limitations are very important. If you don't know the very clearly what is the limitation of this equation and in which condition this equation will applied, you are in a trap. You have to get a very confusing, and you also have a very do a wrong marks in the option A, option B. There is a option, so you can able to tick very wrongly option. Okay, so this is equation. Now beta now we have to take one of these two things. What is that? See, now we take this problem. Okay, this is our problem. Why we are taking this problem? Why? Because beta, see, if we study the first law of thermodynamics, what is the first law of thermodynamics for a process? Stationary, obviously. Sir, dq is equal to du plus dw. No problem at all. Yes. Okay. But sir, what is the use of this equation? Practical use. You can solve any problem. You can solve previous PYQ problem for there are hundreds of PYQ problem related to the first law of thermodynamics. But what is the physical? How to interpret this equation is physically engineering application. See beta, so this is the engineering application problem. There is a fan, you know that this is the table fan. First observe that this is a table fan and fan is running, and during the running air is blowing, okay? And the speed of the outcome air, that means outside, V out, it is given 8 meter per second, okay? Now, what is that condition? We'll just check this. Okay. Let's suppose, see beta, this is the application of the first law of thermodynamics, very important. This is the application of the first law of thermodynamics. See, a fan that consumed, that means a fan, if you buy any electrical device, electrical machines, fan is the electrical machine, refrigerator, air condition, that the power rating on that fan it is given in the downside. If you turn it in the downside, there is a power rating it is given. Sir, at that power it is consumed. So these are provided by the operator. These are provided by the operator, not consumer. So operator gives that, sir, this fan consumed 20 watt. That means joule per second. What is the watt? That means 20 joule per second. Okay, 20 joule per second it consumes of electrical power. When the operating is claimed to discharge air from a ventilated room at a rate of 1 kg per second. That means this says that, sir, it will take 20 kilojoule of electricity and discharge 1 kg per second. He says that. He says that, sir, he says that it will take, that means if this is our system, fine, it is our system, so it take energy, which energy we'll discuss. It take energy, this much amount, 20 joule per second, and gives the discharge 1 kg per second. Okay, 1 kg per second. Now, discharge. And velocity is 8 meter per second. That means output velocity, that means it will discharge, mass flow rate is 1 kg per second, and velocity out, it is 8 meter per second. This says that, okay? Determine this claim is reasonable or not. That means the claim is true or false. You have to ask. You have to define, you have to verify this statement correct or not. Please. At that point, see, if you look this problem, actually this problem, it is not related to any subject. It only related to the conservation of energy, and conservation of energy deals in the thermodynamics first law. So this equation is indirectly related to the first law of thermodynamics for a process. Okay, it is not anywhere mentioned, it is the thermodynamics. Okay, so how to handle with this equation? See, to handle this equation, one second. Okay, see this one, beta. This is our fan, yes or not? This is our fan. Okay, this is our fan. Now, this fan is rotating. Okay, this fan is rotating, and it's blow air to a ventilated room. How much? 8 meter per second. Okay. Now, it's take energy. It's take energy. Let's suppose electricity, I. It's take energy. Now, we have to define, when we apply the energy equation, we first define the system. So this is our system. So this system is a control volume, not, okay, this system is a control volume. That means mass is flowing. Okay, this is the control volume. So these are the system. This is our system. Okay. Now, see beta, we know that energy in, what is the energy in minus energy out? And see beta, the energy, it is given in the form of watt. That means rate basis. Energy, it is given in the form of rate basis. So E dot in, E dot out is equal to dE by dt of a system. This is applicable for any system, and this energy is energy transfer and this is your energy change. Energy change. And what is the assumptions? Just tell me. What is the assumptions, beta? Just tell me. What is the assumptions? This is very important. See, in this system, we have to do a work on this system. Which work? Electrical work. W dot electrical. Why? Because there is an electrical work. We are switch on the fan, and the fan is rotating to take the electrical work. So this is the electrical work. Now, is there any heat transfer from this system? No, we cannot assume like that. That means the first assumption is that what is the total energy giving to the system, that total energy will consumed and it will transfer into the discharge form. This energy in what is the work we have to input to the system, that energy will not a single percent will converted into the heat. Okay, so we can take that no conversion no conversion, the electrical and mechanical energy into heat, that means thermal energy. That means what is the conversion of this energy? It is not converted into mechanical form or any thermal form. Okay, this is the first assumption. What is the second assumption? Steady operation. That means what is the electrical power is input to the system, the same energy will increase the kinetic energy of the system, of the flow. That means what you are giving the energy to rotate the system, that energy will transfer into the kinetic energy at output. That means input is equal to output. If input is equal to output, that means there is no any change of energy with respect to time within the system. That means steady operation, that means electrical work input will equal to rate of the kinetic energy, rate of increase the kinetic energy of the air. These are the important things, basic things, which we will boost your concept. Now, so energy in minus energy out is equal to dE by dt of a system, and this is 0. Why? Steady operation. Okay, why? Because steady operation. So what is the energy in? That means energy in is equal to energy out. Okay, what is the energy in? Electrical. Okay, what is the energy out? In the form of kinetic energy. That means m dot Ke of the air. Okay, so what is the electrical energy? So what is your m dot and what is the Ke per unit mass? Half V of air out. Okay, so from here V out is what? Square root of 2 of electrical divided by m dot. Yes or not? You have electrical work input is how much? This is how much beta? 20. Mass flow rate is 1. So this is how much? This is your C double T, 6.3 meter per second. See, my dear, this is your 6.3 meter per second. But the operator which is operating, he's claimed that sir, this fan gives the velocity output velocity 8 meter per second. So whether this statement is true or false? This statement is false. This statement is false. This statement is false. Okay, that means this is less than 8 meter per second. 8 meter per second. That is, claim is false. That is, claim is false. Claim is false. Agree? So, this is the practical example in which we can apply the first law of thermodynamics, and during that we can analyze the operating system, the situation, given the situation is true or not. Okay, the situation is true or not. So this is the one example. It is a very simple example, but you have a very strong foundation of this one. Why? Because you have to think in this manner. Okay, you can think this manner, how to find, how to relate that equation in the practical situation. Okay, now now go to the next. This one observation is that, okay, 1 second beta. This is your one observation, okay, then we will discuss this third one. So take this first observation. This is your first observation, okay. Now observe very carefully and give me a reply, okay. Observe very carefully beta and give your reply. Okay, observe very carefully and please reply me. Okay. Observe very carefully and reply me. Please, anyone, please. See, what is the observation? All the isothermal process. Which process? Isothermal process. And we know that isothermal process matlab temperature during the process is constant. Temperature during the process is constant. Yes or not? Temperature during the process is constant. Temperature during the process is constant. We know that. Okay. They say that, sir, must be reversible process. This is true or false? Please check. That means all the isothermal process must be reversible process. Please check. See this one. Please beta, reply this question answer. Hey, true. This is true. Okay. This is true. Atul says that, sir, this is true. Atul says that this is true. Okay. This is the beauty of a thermodynamics. This is the beauty of a thermodynamics. All the isothermal process must be a reversible. This line is very important. This is must. This is false. Atul, this is false, beta. This statement is correct. This statement is false. Must. It is given must and all. I will just give you concept. That is the beauty of a thermodynamics. Okay. See. See. Reversible process. reversible process. Reversible process either internal reversible plus external, मतलब internal and external. Reversible, that means internal plus, yes or not? This is agree? Okay. Now, let's check. See, my dear, let a arrangement like that. Let's suppose this is our system. Okay, this is our system, and this is our system, and this system, this is our piston. Okay, this is our piston, this piston. Let's suppose this is our a cylinder, and this is our piston, and in this one there is a system. Okay, this is our system. Let's suppose this is our system. Okay, listen very carefully. It's take 5 to 10 minutes. Why? Because there is a very important concept is here. And let's suppose there is a, this is our system, and apart from this one there is a surrounding. Let's suppose this is our surrounding. Okay, and surrounding have a temperature, let's suppose T0. Surrounding act as a reservoir. We'll discuss in the second law of thermodynamics. And this system boundary have a temperature, and this is have a temperature, this is have a temperature. Okay, let's suppose the system temperature is T1. That means system boundary temperature is T1. Let's suppose system bound. If you ask, if anytime, if anywhere if we say that system temperature T1, you assume that the system boundary temperature. It is necessary that we are taking the heat transfer at a system boundary. We will take, why? Because heat transfer is only the boundary phenomenon. So we define the temperature instead of a system. We define the temperature at a boundary across which the heat will transfer. Okay. So T1, and let's suppose T1 is less than T0. Let's suppose, and if you contact with that, obviously heat will transfer through them. No problem at all. Heat will transfer through them. Heat will transfer. This heat will transfer, let's suppose Q. Now, my dear, and this is our piston. This is our, obviously this is our piston. This is our piston. If it will take a heat, now this creates a external irreversibility. Heat transfer creates an external phenomenon, that means outside from the system. Piston displacement involves internal phenomena. That means this is a dissipation. So there are two things. Expansion of a boundary, that means boundary will displace the piston, there is a boundary work. That means here, this is from this boundary there is an energy transfer. This boundary there is an energy transfer. This boundary there is energy transfer. So this boundary there is energy transfer due to internal mechanism. This boundary the energy transfer due to external mechanism. Why? Because system is an internal. We'll just go, we'll just out, coming. We have just create a surrounding, we create an environment, okay? I will come, Atul, I will come that point. Just be patient. It will take little bit time. So there is a two type of energy interaction. There is a work interaction, there is a heat interaction. Work interaction due to displacement of a boundary, and that is internally. This is heat transfer due to externally. So there are, you just keep in mind, there are two energy transfer due to two mechanisms. First due to system mechanism, due to the system, and second due to the surrounding. So this may it call internal, and this may call it will external. These two things It is very clear. Okay, no problem at all. No problem at all. Now come on your point. See beta, if T1, we want the process is isothermal. We want the process is isothermal. If we want the process is isothermal, T1 must be constant. Yes or not? At any time, at any location, the temperature is constant. That is called isothermal. At each and every point, when the system will execute, throughout that point, that means if this is our thermodynamics plane, this is your y and this is your x, and this is your isothermal process 1 to 2. So between all the points, temperature is constant. See, my dear, that means at this point temperature T1, 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 at this, all the point. It is not like that, sir, 1 and 2 the temperature is same, so throughout the temperature is same. No, isothermal, that means isothermal. All the points related to, linked between initial point to final point, all the points the temperature is constant. We want like that. Number third point. This is number first, this is number second, this is number third. Okay, now next. That means isothermal process for a system and it is that. Now, see, if you want that internal reversible, due to isothermal, we want that the temperature is throughout constant. At any mechanism, we have to keep it, temperature T1 is constant. Now, come the internal reversible. Why? Because if you want the reversible, that means we want internal as well as external. Okay, very carefully. We want that internal as well as external. Now, if we do the internal reversible, what is your mechanism? What is your thoughts? That means the piston will move in a quasi-equilibrium process. Must be. That means if you want the system is reversible, that means the system is internally as well as externally. Now, this is the third point, this is the fourth point. Fifth point is that if we want the system is internally reversible, the system process will execute must be a quasi-static manner. How to make a quasi-static manner? That means there is no any friction dissipation loss. When we have a make a situation like there is no any dissipation effect, there must be a piston will displace in a very slow manner. That means if this energy transfer is the boundary work P dV, that means 1 to 2. In that condition, this is internal reversible. Must be internal reversible. So, now, come to the external reversible. See beta, if we want the isothermal process, that means system temperature is fixed. So it may be we increase the heat transfer at a very fast temperature difference. That means when it is external reversible, first tell me, when it is external reversible temperature, that means system temperature T1 tends to surrounding temperature T0. That means T0 minus T1. Yeah, T0 tends to T1 tends to 0. That means delta T tends to 0. That means heat will transfer through a very infinitely small temperature difference. But it is not like that. This heat will transfer maybe finite temperature difference, maybe infinite temperature difference. If we make all the isothermal process must be reversible, it is not necessary. always true. No, it may be false. Why? Because there may be heat transfer through a finite temperature difference. Through a finite temperature difference. If the heat transfer through a finite temperature difference, so how can you say that the system is reversible? If the difference between T1 and T2 is very large, yes, you are right, Prabhu. If na, but it is not necessary na. Hi Sita, how are you? Okay, so Atul, I repeat, if difference between T1 and surrounding temperature is very low, yeah, very infinitely small, then we can say that. But there is a if, it is a fixed statement. Got it? It is a fixed statement. All the isothermal process must. No. If disregard the must, that means all the isothermal process, instead of must, may. You write may. May be reversible process. Yes, then you are right. Instead of must, if you write may, then you write. But there is a must. It is not must. Why? Because heat will transfer through a finite temperature difference also. It is right? Clear? Is it clear? So we'll take this one as a statement, okay? This is very important, I'm telling you. This is very important, okay? So, see this one, right one. I will write this thing. Literally, this is very important, I'm telling you. Many students get confused here. So that I will write this thing, okay? Clear? Okay, Pratik. Okay. Just see this one. Just see this one. I will write complete statement so that you can never get confused. Why? Because in my experience, once such type of things are come into your picture, now come in front of you, you are very much clear at that point. But after some time, you have forget this thing. You have forgotten this thing. So you write these things in your notebook so that again and again you can repeat. So you have to got a very strong foundation of this one, okay? Right, okay. See this one? See, my dear, see. Now, this is our surrounding, okay? This is our surrounding. Surrounding have a temperature T0. This is our system. This is our system. System temperature is T1 is less than T0. Obviously, heat will transfer Q. This is your system, okay? Now, if, see beta, if it is visible, yes, if the piston, very important, if the piston move very slow, that means internal reversible. Internal reversible. That means quasi-equilibrium process. Quasi-equilibrium process. Okay, now, but if T0 minus T1, very important, if T0 minus T1 is equal to finite, not infinite. Finite temperature difference. Finite temperature difference. So, what does it mean? So, may be external reversible. May be, very important, external reversible. May be external reversible. Right, Pratik. Piston move very slow means it will follow infinite step. That's why a reversible. Very correct. That means you have to know each and every step at equilibrium point. That means we are moving from my office to my home at each and every equilibrium point. That means we are moving some distance and then stop. Again we are moving, then stop. Again we are moving, then stop. Accordingly, we have a trace a path. That is called thermodynamics process. You are right, Pratik. You are very right. So, may be external reversible. Hence, isothermal process may be, very important, may be internal reversible, but it may not be, but it may not be total reversible. Total reversible. This is very important, I'm telling you. May not be total reversible. Now, how to make a total reversible? How to make a total reversible? That means piston will move in a quasi-equilibrium process plus heat will transfer through infinitely small temperature difference. That is the total reversible. In that condition, if you maintain the system temperature fixed, that is called reversible isothermal process. Okay? That's why in Carnot engine, in Carnot cycle, one process is isothermal. That means we have to make the process totally reversible. That means internal as well as external. That means you have to apply that concept through a Carnot model. In the Carnot model, we transfer a heat through infinite small temperature difference, and also we move the piston very slow so that the whole process is reversible. That is called reversible isothermal process. Reversible isothermal process, that means total isothermal process, that means internally as well externally. It is clear? It is clear? Okay, na? Right. This point is very clear. That means isothermal process may be internal reversible, but it may not be total reversible. Why? Because heat will transfer through a finite temperature difference. If this temperature is very high, the heat will transfer through a very rapid manner, so that the system will externally irreversible. So if the system is externally irreversible, then the whole reversibility is vanishes. That means ultimately the system is irreversible. Okay. So if we want that, if process is quasi, process is, okay, no problem. If process is quasi equilibrium, that means internal reversible, and T naught minus T1 is equal to delta T, and this is tends to 0. That means infinite small temperature difference. So it is external reversible also. Hence called total reversible or reversible process. Okay, means what is Pratik? Means the game is all about temperature difference, very small. Okay, if the higher temperature exists, then the reversible system is turned to be great. You are right, Pratik. You are right. That means, beta, this is very important thing is that we have to confuse that always. Ki sir, if the process is quasi, next observation is like that. This is very important. Next observation, that is the next observation you have to clear about your statement. What is that, beta? It is not necessary that the internally reversible, that means the total reversible. No, if you make that it is not like that. If you control the transfer of heat through a very infinitely small temperature difference, so it is a reversible. No, again you are wrong. Reversible, that means you control the heat transfer through an infinitely small temperature difference. Always there is no any dissipation. That is called total reversible. That means game is all about no, it is not. Game is all about the temperature difference. No, if the see, it is not like that. See, if the temperature difference is very infinite, see my dear, if the temperature difference is very infinitely small temperature difference, very infinite, so you have to make external reversible, no problem. But it may be the system is, it may be the system is, you started the system. If you started the system is internally irreversible. So heat will transfer reversible, but the system will perform a work in irreversible manner. So the total is irreversible. Like that, see this example. If this is your piston, see cylinder, see this example, very important thing. And if you transfer a heat through very small temperature, that means delta T tends to 0. So delta T tends to 0, that means external reversible. External reversible. Now you are churning the system. Now you are churning the system. So the system external reversible but internally irreversible. It is also like that. It is right, Pratik? So it is a not a total reversible. It is right. So we'll take a next. Thank you, Sandeep. So it is not like that, ki sir, all about the temperature. No, it is not like that. If the temperature is small, maybe externally reversible, but internally irreversible. Why? Because there may be a chance that you transfer the work from the system to the surrounding, a surrounding to the system through a paddle wheel or any churning device, so that the dissipation will take place. If you control the dissipation, also you have control the heat transfer through an infinitely small temperature. In that manner, you called that the total system is reversible. Okay, take this one. This is true or false, please. This is true or false, please. Anyone? All slow process must necessarily be reversible. Please. This is true or false? This is true or false? Anyone please? False. Yes. Now you have to clear. This is also false. Right, Pratik? Now it is clear, na? This is very right. Now you think. Now you think your approach. Okay? And write your comment. I will explain you. I will explain you, beta. Write down, I will explain you. Okay? Explain. See, this is regarded all slow process must be necessarily reversible or not, it will ask. See, you think that the slow process is a quasi-static process, so it is reversible. No, it is internally reversible. It is right that all the slow process must be. Slow process, that means either heat will transfer through a very infinitely small temperature difference. If the temperature difference is large, process, that means the transfer of heat is high, rate of transfer of heat high. If the temperature difference is very minimum, so the process is slow. If the piston will displace very slowly, the process is slow. So all these things, all aspects you have to clear about that. All slow process, all type of slow process, either heat transfer, either displacement of a boundary, any type, that are the slow. Then this is the reversible process. See, if we take any process 1 to 2, during which the piston will move very slowly, but the heat will transfer very fastly. So it may be internal reversible, but external irreversibility. So the total reversibility condition will vanishes, and ultimately the system will execute in irreversible manner. So it is not necessary. I will write that because all slow process must be in general internal irreversible. Internal reversible, but maybe external, but may not be external reversible, but may not be external reversible. So if they are external reversible, that means the net process becomes irreversible. Yes or not? The net process becomes irreversible. So, see my dear, this is very important. See, this is very important. I will give you one shot. See it. See this one, very important. This is very important. What is that? Reversible process that means it has to very important, I'm telling you, internal reversible or total reversible. And what is the total reversible? Internal plus external. Internal plus external. That means a system reversible, the condition for the reversible, it is, see, it must be internal or total. If, see my dear, very important, if the process, see very important, if the, listen very carefully, this is the golden word, this is the golden line. If the system is internally reversible and externally irreversible, I repeat, if the system is internally reversible and externally irreversible, that is also quasi-static process. That means quasi-static process is a reversible process if and only if there is an internal reversible or total. This line is very important. That means where is the reversible process? That means you have to draw a thermodynamic plane. There is a thermodynamics plane and you have to draw any thermodynamics process. That thermodynamics process is a reversible process. That thermodynamics process is a reversible process. And that reversible process must be internal or total. That means that thermodynamic process must be a quasi-static process. I will already discuss. We already discussed this thing. That means internal, if you made the internal reversible, you have to disregard the dissipation effect. Disregard the dissipation effect. Okay, so this is total reversible. Now, the internal reversible, this is very important. Internal reversible must be quasi equilibrium, quasi-static equilibrium process. Quasi-static, you may write like that, no problem. Quasi-equilibrium or quasi-static equilibrium process, no problem. Quasi-static equilibrium process. This is very important. Now, this is very important, quasi-equilibrium process. But quasi-equilibrium process need not be reversible. This is very important. Quasi-static process need not be reversible. It is must be internally reversible, but internal reversible need not be reversible. Why? Because there may be external irreversible. Why? Because there may be external irreversible. This is very important. That means must be quasi-static equilibrium process, and quasi-static equilibrium process need not be reversible because it can be external irreversible process. That's it. That's it. It is clear? This is clear? Everyone, please. This is very important, I am telling you. It is clear? Pratik, it is clear, beta? It is clear? This statement is clear or not? Please reply, everyone. This statement, whether it is this statement is clear or not, please reply, everyone. Yes, I am thinking. You are thinking. You are thinking. No, It is very clear. Why you are thinking, where you are thinking, I don't know. Yes, it is very right. You are just think and find your very accurate conclusion for that one. Okay. Why? Because this is the beauty of a thermodynamics, where 99% students and also 50% teacher get confused. I'm telling you. Okay. If there is any confusion, you have to feel free ask to me anywhere, anything. Okay. Now, so today we will stop here, and after that, in the next section, if you have any query, Pratik, just come. Tomorrow we'll again have a sessions. You just ask me, okay, and post your comment. Also, no problem. And I know this is if you if this statement you see you have a listen very first time, yeah, you have to feel very first time. It is very difficult to digest. I know. As a teacher, I know there is no any problem. So you think you have a lots of time. Thank you. Bye bye. Take care.